Uh, Good morning, everybody. So in previous discussion, we had discussed regarding introduction to digital signal processing, and I think we have discussed convolution and Z transform, what is meant by DFT, FFT, and what is meant by LTI system. So we had discussed what is actually a digital filter, and we had seen the equation for this. So as we had discussed previously, just a recap of the previous session, that is in which we discussed digital filter. Filter is one which removes unwanted stuff from the sequence in case of discrete signals. Now, since we are speaking of digital, the term comes as sequence over here, and the type of filter is can be basically identified based on the impulse response which is present for that system. Now, in a different way, if I have to define the digital filter is one which accepts the input sequence x of n and generates some filtered output sequence based on the impulse response of that system, that is sequence h of n. And now, generally, when we want to represent filters, right, we can represent it in a difference equation when we are speaking of digital filters. So in this one, this was the equation, difference equation, which we had used to represent the overall digital filter. So this is a general expression. And in this case, one important thing which we have to identify is the coefficients. So if I am able to identify these coefficients, using these coefficients, I'll be able to obtain the desired filter. Now here you can just observe that this is the summation with respect to the shifted versions of y of n. That is, it is the previous output. This is the previous output, and this summation includes the shifted versions of the input, which is nothing but the previous inputs. So this is just a general representation. It is a general representation. Again, in this, again, we have two kinds of filters. One is called as FIR and the other one is called as IIR filter. So FIR filters, in short, if I have to tell, it is dependent on only the input, present input and the past input values. It is not dependent on the past outputs. Whereas IIR filter is dependent on the present input, the past input and the past output. That is all three together. So if I just observe for FIR filter, this entire summation will not be present. So in short, if I just specify, these coefficients will be 0, turning out to be 0. But in IIR filter, this is not assured. This can have a non-zero value. This also can have a non-zero value. So this is the general equation what I have to remember. And this general equation, when I present it in a say as a block diagram, this is how it is represented. That is, I have x of n and y of n, and in between the entire equation you have to fit in. So here we can see that it is the this is b0, this is b1, b2, so on up to bl. So this entire thing is obtained based on the equation, and this is the coefficients ak. These are the coefficients ak. Now here unit delay, if I'm speaking of say for example digital domain, right, if I pass say a sequence through a block as e raised to z minus 1, then it is, I'll be getting a delayed version of the input, that is x of n. I'll be getting a delayed version of the input, that is x of sorry, n minus 1. So that is what unit delay specifies in the digital filters. So this is the block diagram representation of the general equation what we have presented here. So k is from 1 to n and coefficients are a1, a2 up to an, and here if I just observe, it is y n minus 1, n minus 2 up to n minus n. So if I see the block diagram, I'll observe here yn is already present. What are the remaining? I should have yn minus 1, yn minus 2, so on up to yn minus 1. And what are the coefficients I'll be having for this delayed version? Coefficient is a1, next is a2, an minus 1, and last one is an. So these are the coefficients related to the output sequences. And when I come to input, I have coefficients bk, and k is very from 0 to l. So here it is x of n minus 1, n minus 2, so on up to n minus l. And this coefficient with respect to that term multiplied with that term, that it will be b0, b1, b2, so on up to bl. So this is with respect to input side. So this is b0, b1, so on up to bl. So b0 is multiplied with x of n, and then it is added with the next one, that is x of n minus 1 multiplied, this parameter will be multiplied with b1 and then added to the previous, so overall result gets added here. So these are the summations what I'm getting. So it will be xn minus 1, n minus 2, so on up to xn minus l. So here bl and all the coefficients get added over. So here if you just see how many adders would be present, you can just make out. So generally what you do is when you're speaking of digital signal processing, right, you try to reduce these kind of hardware structures. So if you're able to reduce these kind of hardware structures, if you're able to do that, then what happens is you'll be reducing the overall computation time. So that is what you try to implement in DSP. That is what you try to look out. That's why you have a separate processors for those things. So wherein in your lab, right, in your Verilog lab, you might have gone through FPGA, right? So FPGA is a kind of digital signal processing block, so which helps us to compute the parameters at a very fast rate. In that, I think you might have done convolution and other stuffs. So those are the DSP aspects what you have implemented. Apart from that, the regular expressions also you have implemented, that is the logic design aspects. But with respect to DSP, few of the programs you had implemented over there. So that is a DSP FPGA kit would help you to implement these kind of things at a very faster rate. So you have a programming blocks over there. So you can use those, program it as per your requirement, and see how you can reduce the overall computation time. That is what you try to achieve. Next comes the first topic, that is FIR filter. It is finite impulse response filter. So the name itself tells that the impulse response has something to do with finite aspect. So here impulse responses will be of finite lengths. So in FIR filter, impulse responses will be of finite length. And what is the present output dependent on? The present output is dependent on the past values of the input sequence and the present values of the input sequence. So here if I just observe, it is not dependent on the past values of the output. It is totally dependent on the input, present input, and the past values of the input sequence. So if I go back, that is we term this to be non-recursive and inherently stable when this kind of condition comes in. That is, if it is dependent on only these parameters. Now here present output does not depend on the previous output sequences. That is what I had specified in the previous slide also. Now if I go back to the previous slide, right, in this equation. So what is the specification given? That output, present output, is dependent on present input. So if I just put k is equal to 0, what happens? I'll be getting x of n. X of n is the present value. X of n is the present value. If I go on substituting the others, what happens? I'll be getting x of n minus 1, x of n minus 2, so on up to x of n minus l. So these all are the past values. And another specification given was this output does not depend on the previous output. So that is, this term won't be present in the FIR filter response equation. So this is what it appears. Now even if you look at the block diagram, you can just make it out. So here if I just observe, So this is the present input, and this output is so this present input is say moving from this point to this point. If I just observe, y of n is also dependent on this. So this is the present input. It is also dependent on these factors, so which are nothing but the previous versions of the input or previous values of the input. Therefore y of n is dependent on present input and the past input values. It is not dependent on the past values. So in that case, what happens is there will be some modification in this part, since this entirely has to become 0. So this part won't be there. So it will be directly, say for example, it will be y of n here itself. This part won't be present. It will be y of n, which will be obtained at this point. So as discussed, finite impulse responses will be of finite length. The present output depends on the past values of the input sequence and the present values of the input sequence. It does not depend on the previous output sequences. So when I represent this in the difference equation, what happens is only the second term remains. That is this equation what we are representing here. That is the present output is dependent on the present input. When I substitute k is equal to 0, I'll be getting the term as x of n, so which is the present input. When I go further, I'll be getting x of n minus 1, so on up to x of n minus l, that is up to this value. So these are all the previous values. This is the present value of the input, and I have to identify these coefficients. I know the input, I have to identify the coefficients and what response. Say if I'm giving a say a step response, so how the system responds to a step input signal. So that is what I try to identify here. So the equation in which the other part turns out to be 0, and this is the FIR equation, FIR filters equation, difference equation. Now such kind of filters, right, they generally have a linear phase response. So this actually helps us to be utilized in some of the applications which are not tolerant to any change in the phases. If there is slight change in the phase, then the output won't be in a proper form, or it would not be in the intended form. So in such applications, right, we would like to go for FIR filters. Now FIR filters, in this case, the unit sample response of the FIR filters lasts for a finite time depending on the coefficients. It lasts for a finite time. This is also another reason why it is called as FIR filter. So that is the unit sample response with respect to this filters. When particular input is given, it will be of finite time duration. That is finite time duration. So therefore, and it also depends on the number of the coefficients bk which are present in this case. So the depending on these, we'll be having the finite response, unit sample response. So hence the filter is named as finite impulse response. One is impulse responses are finite length, and another this thing is in FIR filters the response lasts for a finite time duration. So that is another reason. Now we had seen that frequency response. We had seen in previous slides how we can obtain a frequency response. So if I know Z transform, how I can obtain frequency response. If I know frequency response, how I can obtain the Z transform. So it is invariable. It is say interchangeable. So in for example, if I just observe this, so this is a general equation which we have. If I have identified the coefficients, and if I want to see what is the frequency response of this filter, then this is the equation what I use in order to estimate the frequency response. So wherein it is h of e raised to j theta, and since I am having coefficients from 0 to L, so I'll be having only those many terms. Remaining all will be 0. Even if you write it as infinity also, remaining terms are 0. So there I'll not be getting any output in those cases. So I can limit it up to L, and e raised to minus j k theta, where theta is the digital frequency, and even sometimes Z is also termed as the digital frequency equivalent. So here, so this is the frequency response equation using which I can obtain the frequency response of the FIR filter. Now, if I want to modify and get the Z transform for the same, it is nothing but just replace e raised to j theta with Z. So e raised to j theta, if you replace with Z, what you are getting? So here e raised to j theta minus k remains. So Z raised to minus k. So this is Z transform related to the frequency response equation what we have seen here. So this also we can term it as the transfer function. We can term it as the transfer function, since h of z is nothing but ratio of y of z divided by x of z. So finite impulse response filter, what are its features or characteristics? First of all, it is a stable filter as it has no feedback in this case, because y of n, all those stuffs are not present. There is no dependency on the previous outputs. Present output is not dependent on the previous output. So hence we classify it to be a stable filter. Next, what happens is this is a symmetric coefficient FIR filter. Because of this, right, we have linear phase response or constant group delay. We observe linear phase response or constant group delay in FIR filters. Now this is what I discussed in a previous slide. That is, we can use such kind of filters where a phase distortion is not permitted. So if some phase distortion happens, then the entire system will not be operating in the intended form. So in such kind of applications, I can go in for FIR filters. Now, what are the disadvantages of such kind? Now, whenever some simple thing is there, then I'll be having some other cons which comes into existence. That is, if I want to have some intended frequency response, then it might go in the form that number of coefficients which are present. In order to estimate those, there may be a large number of coefficients which I have to calculate or estimate. Now, if more number of coefficients are present, then what happens is it naturally increases the computation time. So if you're increasing the computation time, you're utilizing the hardware for a more amount of time. So if you're utilizing the hardware for more amount of time, then what happens is invariantly the power dissipation also will be more in such cases. So these are just a few things to name. Now, because of these two aspects, right, what happens is it puts some limit on the sampling rate and the bandwidth of the signal that can be processed. So it puts limit on these things. I suppose if the bandwidth is too high, then it might lead to very large number of coefficients to be estimated for a FIR filter. So in order to cater to this, then we this imposes the limits on the sampling rate and the bandwidth on the signal what you will be processing. So we saw these things. That is discussion regarding the FIR filter advantages, disadvantages. Then let us see one problem related to FIR filter. So here we have a FIR filter which is given by the difference equation. Now, first thing, how do I identify that this is a FIR filter? So if I just look at the output, right? If I look at the output, it is dependent on, say, the present input and the past input. So only one parameter. So when I see a difference equation of this kind, it specifies that this refers to FIR filter. It is not dependent on the previous output. It is not dependent on the previous output value. Now this equation basically defines a FIR filter So if I just observe, it is nothing but x of n plus x of n minus 1 divided by 2. So it is nothing but it is taking the average. Average, say if input is the current x of n, what we are specifying, and past one input. So this is nothing but average equation. So that doesn't matter. It is just a representation of the equation. So it is dependent on present and the past, one of the past values of the input. And so when I take this case, it is a FIR filter. Now, if I have to obtain its frequency response, right, then I have to go ahead and just try to see how I can solve this entire equation. Now here what I'm trying to do is I'm trying to have a unit sample response of this filter. So when I want the unit sample response, I'm just substituting the input with delta n. That is, here I'm considering input x of n is equal to the impulse value delta n in order to obtain the impulse response, how the system responds to the impulse input. That is, impulse is nothing but delta n. So when I substitute it over here, what happens is I'll be getting 0.5 times delta n and 0.5 times delta n minus 1. So when I think you might have, know how do you represent these signals when you have the samples. So this is the sample at the 0th location or the first sample, and next sample is also 0.5. So which is at the first location. So when you have discrete sequences, right, this is how you represent it. So that is what is represented here. So this gives you the overall response, that is h of n. So h of n is 0.5 comma 0.5. So this is the sequence for this equation, difference equation. Now once I have got this, next what I want to do is I want to obtain the frequency response. I want to obtain the frequency response for the impulse, this thing what we have obtained, or frequency response of the filter what we have. So it is nothing but you use the previous equation, that is h of e theta that is this equation. You use this equation, h of e theta is equal to this parameter. But in previous slide, right, we had obtained another one equation, that is h of e theta is equal to summation xn into e raised to minus j theta. So even that can be utilized. That is the equation what we have to use, wherein this frequency response is equivalent to summation x of n into e raised to minus j theta, and these limits depend on how many values are present. So when I refer to that, what happens is if I substitute it in that equation, I'll be getting this entire stuff, that is h of e raised to j theta, which will be equal to summation of h of n into e raised to minus j theta. So 0.5 into delta n parameter which is there, so that is I'll be having 0.5 into e raised to j0. So it will be 0.5, and it will be 0.5 into e raised to minus j theta into 1, j theta into 1. So it will be 0.5, since the first value is that one, into e raised to minus j theta, k is 0 over here, plus 0.5 e raised to minus j theta, and k is 1. So therefore this turns out to be 0.5 plus 0.5 into e raised to minus j theta. And when you solve it, you take e raised to j theta by 2 common. So when I just subdivide this e raised to minus j theta, I can write it as e raised to minus j theta by 2 into e raised to minus j theta by 2. And when I take it out common, what happens is this term, that is when I take e raised to j theta by 2 common in these two, it turns out to be 0.5 into e raised to minus j theta, e raised to plus j theta by 2, and this one will be 0.5 times e raised to minus j theta by 2. And when I solve it, I can represent that equation in terms of cos, that is cos theta by 2. Now when you have equation in this form, right, if you just observe, if I take the magnitude of this and the angle of this particular equation, that is the phase, I'll be getting the magnitude response and the phase response. I'll be getting both. So here I have got this equation. Now, if I want the Z transform equivalent of this, substitute e raised to j theta as Z, you will be getting this equation, that is 0.5 plus 0.5 times. So e raised to j theta as Z, so it will be Z raised to minus 1. So this is what I'll be getting. Now, how do I obtain the frequency, magnitude response and phase response? So what I do is, this equation I consider and I take the magnitude of this entire parameter. So when I consider the magnitude of this, what happens is, I can again bifurcate, that is, if I have some term like a into b, if I take the magnitude of this, it will be much lesser equal to magnitude of a into magnitude of b. So something in this form. So this is like a and this is like b. Now if I just observe what is magnitude of a, that is exponential, is always equal to 1 in here. It is equal to 1, and magnitude of this one is dependent on the theta value. So therefore magnitude of this will be equal to cos theta by 2. Therefore what happens is, this is 1 into cos theta by 2. Therefore the magnitude response is equivalent to cos theta by 2. So this is how it happens. If you have any other method, you can use that method also. Suppose I think you can take, you can divide this into say real and imaginary parts, and that is a plus jb. And if you want to identify its magnitude, so this is actually in the form of r into angle theta. It is in this form, where r will give you the magnitude, this thing, which is this part, and the theta is obtained from this part with the other factors. So it will, what you do is, if you want to identify, you can either go directly, or you can identify it using this one, a plus jb. So if I want magnitude, it is square root of a square plus b square, if you remember. And if you want angle, right, you can use a calculator and estimate it. If you want angle, right, it is tan inverse of b by a. So this is another method of obtaining the phase. So now here what happens is, since they are in polar representation, what is the phase response due to this, plus, since it is in multiplication, plus the phase response to this. So therefore it turns out to be addition. So in this case, right, the phase of e raised to minus j theta by 2 is equivalent to minus theta by 2. So this is with respect to the first term, plus additional phase which is provided by this cos theta by 2. What will be the phase provided by this? So both together will be giving me the phase response. So this is magnitude response, this is phase response. So now if I have to estimate what is the group delay, what I do is, I differentiate and negate the phase response function. I differentiate and negate the phase response function. So if I want to estimate the group delay, I have to make use of this equation. That is the phase response. You differentiate this equation with respect to theta, d by d theta. So when I take d by d theta of this, what will be happening is, this will be turning out to be 0. And here what it happens is, this will be turning out to be minus 1 by 2. Now I have to take inversion of that, that is minus d by d theta. So when I take minus of minus, this turns out to be plus. Therefore, this is the group delay for the given difference equation what we have observed for FIR filter. So if I have to see how the block diagram appears for this case, right? So this is how it can be represented. How this is obtained. How this is obtained. So this is obtained by substituting theta value and trying to see some intermediate values. You just substitute. Say theta is equal to 0, how much? Theta is equal to 30 degrees is how much? 45 degrees is how much? 60 degrees is how much? And then intermediate values you just approximate and try to obtain it. So that is one method. Or else if you know how the curve appears, you can use it directly. Say if you have a tan curve, how the tan curve appears. So if you know that, then you can directly use those. So that is how you try to estimate these things. That is how you try to obtain the plot for the magnitude response and the phase response. Now this block is obtained based on the equation. So the equation was y of n, which was dependent on zero point 0.5 into x of n plus 0.5 into x of n minus 1. So this was the equation what we had. So here I am having x of n. I should have x of n. So I can have it by passing it through a unit delay. Say for example, it might be the z inverse block. So which is related to unit delay. So I'll be getting x of n minus 1. Now what should be the multiplication factor for x of n? It is 0.5. So I'll be multiplying 0.5 to this and I'll be giving it to the adder. I have to add it to what? I have to add it to 0.5 times x of n minus 1. So therefore 0.5 times x of n minus 1 also comes here and gets added. So once these two signals are added, I'll be getting the overall y of n. So which is the FIR filter equation what we have represented. So this is a block diagram related to that. So this is all related to FIR filter. So in next section, we'll be discussing regarding IR filter and then proceeding further with the remaining